We got this filter right here, circuit theory, and let's see what we can do. The problem says to classify the filter. It was given to me just like this. So normally when they say classify the filter, if you have like, it'll be given in this kind of like 2-line parallel arrangement, okay? And if that's the case, then generally we like to build them so that the left side is the input and the right side is the output. And so now if you kind of can set up classify the filter, now we say we have input versus output where their voltages, we can try to see what it would be because it's all about looking at the transfer function, right? So normally it would just be something like that where it'd just be the R, the L, and the C, and that'd be fine. But in this case, we have this R right here that's going to stop us from really doing it the easy way. Normally I would just try to kind of set up like a voltage divider or current divider and then go from there, but the voltage divider gets wrecked by this, okay? So because that messed me up, see if I can do it like a different way. Because I'm just looking to classify the filter, I think what I'm going to do is I'm going to kind of dodge the math and just go conceptually. All right, so we'll say concept. And so looking at the concept, let's look at how the frequency, because the whole idea behind a filter is you're looking at the frequency response, right? That's what it is, the frequency response. So I'm just going to look at how frequency affects capacitors and inductors. So if we take an inductor, I know in AC, the equation for an inductor is JWL, right? All right, that's fine. Well, when W is close to 0, we like to say, if we call all of this the impedance, we like to say the impedance of the inductor approaches 0. All right, when W approaches infinity, we like to say the impedance of the inductor approaches infinity. Okay, if you just plug in W as 0 at different values, you're good to go. And so let's take a look at what the impedance being 0 and infinity represent. Remember, impedance is frequency resistance, right? So we're going to say this is basically a 0 resistance to frequency, no resistance. Okay. And so when I say no resistance, if you think about any element that has no resistance basically corresponds to a short circuit. A short circuit has 0 resistance. And so what that means is that there's no voltage across. There's no voltage across it, but there is going to be current. Okay. And so when you're looking at your signals, you have to kind of understand what that means. What that means is if I were looking at the voltage side of things, then this is not going to allow the voltage to pass by. However, if I were looking at the current side of things, right, the current is going to exist, and so the current is going to pass by. And so that's what the inductor does when it has 0 frequency. When it's infinite frequency, infinite frequency. When you have infinite frequency, you have infinite impedance, and infinite impedance basically says you have all the resistance in the world, like infinite resistance. Okay. Infinite resistance basically is going to be written as an open circuit. Okay. A lot of students, I just tell them, whenever one thing does one, the opposite behavior is going to give you the opposite. So at 0, you got to get a short. At infinite, you probably want to get an open because they're opposite elements. And so with infinite resistance, I equals 0. All right, so you have no current passing across the gap. But there is a voltage there. We don't know what it is, but there is a voltage there. And so what that means is the voltage is going to exist, but the current is not. And so we can take a look at the passage, like the passability of the transfer function with the inductor. Take a look at the capacitor. You get the same thing up backward. So you get 1 over JWC. And so when you go from W approaches 0, Z of the capacitor approaches infinity because they have the opposite behavior. And when W approaches infinity, the Z of the capacitor approaches 0. And so what this is saying is when the frequencies are low, the capacitor acts like an open circuit. Okay. And it makes sense conceptually if you look at it from another point of view as well. I'm just not going into it. But think about how a capacitor would charge and discharge. Basically, what they're saying is if your time constant is like really, really big, the capacitor can, if the time constant is really small, and you don't really vary the voltage across the capacitor, then the capacitor is gonna fully charge and fully discharge, all right, over the range when there are small frequencies because the frequency is not changing fast enough, all right. And so what happens is the capacitor acts like an open at low frequencies and acts like a short at high frequencies. So let's take those ideas and then use that to classify this filter. And that way we can get the answer without having to do too much mathematics. So we'll compare. So we'll do, I'll put it in purple, I guess. So we'll say compare. And we're going to compare the low frequencies to the high frequencies. And so I'll compare when W approaches 0 versus when W approaches infinity. And I'm just going to draw two circuits and see what the answer gives me in terms of the output, if it's a feasible thing or not. So when W goes to 0, I got my resistor, because resistors, don't do anything. And I know at low frequencies, the inductor is a short and the capacitor is an open. And so I'm going to write those like that. Okay. The inductor shorts, but the capacitor opens. And so that's what you have. Okay. So if you take a look at the voltage, this is my output and this is my input. You're going to have an input. That's the whole idea. You put an input. So the voltage is going to kind of exist on this side. The whole idea is, can you measure a voltage on the output if you have this short and open here? Well, yes, you can. Because think about it. There is no voltage on this piece. However, there is a voltage across this piece. Okay. And so basically the voltage of the capacitor is gonna lend itself to becoming the voltage of the output. Okay. If you were to kind of put it in blue, the voltage of the output will be the voltage on this resistor plus the voltage from the capacitor to the ground as such, like this. So trace the blue line, that's going to be where the voltage out goes. As long as you have a measurable voltage there, you're good to go. And so because I have a voltage on my capacitor given as a yellow highlight, there is a output voltage. I'm gonna put a little check, and that means that it's passing. And so at low frequencies, you have a pass. I like to say it passes. There's an output voltage that exists. If it exists, just say it passes. At high frequencies, you're gonna have the same thing, but different behavior, but they work backward. And so you take your two resistors, all right? And this time, you're gonna have the inductor, which opens up, but the capacitor, which shorts out. Well, it's the same exact thing, okay? Except in this case, the inductor has the voltage, okay? And so if you measure the voltage here, you're gonna get a voltage on the resistor, all right? Assuming that there's current that passes by. And then there's gonna be a voltage that takes you from the top node right here to the bottom node right there via the inductor. And so what happens is the output voltage still exists, okay? It would only not exist if there were a short, and I'll draw that up in a second. So let me just see. VN. And so what happens is this circuit also passes. And so if you think about it, there are only four real types of filters. You got your low pass, okay, and in your low pass, the high frequencies go in. It's ugly. I'll just kind of do an idea. In the low pass, you have your low frequencies that pass through, but the high frequencies don't. You got your high pass. And in the high pass, your high frequencies pass through, but your low frequencies don't. You got your band pass. And in your band pass, you have a specific range of frequencies that pass through, and then everything outside of that doesn't. So an entire band passes. And you have your band reject. And the band reject is the opposite of the band pass. So everything except a specific band of frequencies passes through. And so if you think of the high point as the pass, okay, and the low point as not passing, then we have a situation where at low frequencies we pass and at high frequencies we pass. So mind you that this bottom axis is the frequency axis, okay? And so the only one of these that satisfies that is the band reject. At low frequencies, the band reject passes, and at high frequency, the band reject passes. And so it looks like this filter is a band reject filter, okay? This filter right here, I'm gonna say is a band reject without doing any real math. It looks like our answer is band reject. Oh my God, that blue did not work well. So I'll just put a blue. There we go. Band reject is going to be the answer that we pop with. So one quick aside, how we know, like, how do you figure out based on this circuit, when is it going to be the case where the voltage doesn't pass, right? So because of the way this is built, that's never going to happen. Basically, what you need to create a situation where the output voltage doesn't exist, the only time the output voltage won't exist is when it's equal to 0. And the only way that that can be is if you have something like this. You get your resistor, and then your capacitor and your inductor both short. Okay, they both short. And then when they both short, somehow if they both short, what's going to happen is this. If you take a look at the current's going to come here. And because of this short, it's not going to go this way anymore. It's instead going to go straight to the ground. Okay. All of the current would do that. And when that happens, this resistor would effectively die away. Okay. Because it would get no voltage, no current, no current. And if it has no current, then it has no voltage because of Ohm's law, which would basically say that the output, because there's nothing here, there's nothing on this blue line, this blue highlighted section that would have volts, the output voltage would be 0. Oh, not check, excuse me, but 0. And if it were 0 in this case, then we could say it's not passing, right? But because of the way that the capacitor and the inductor are set up, one's got to be off while the other one's on. And because of that, you're always going to have a pass. And so in this case, we're going to have a band reject. Okay? So that's the scope of our problem. Did it without really doing any math. I kind of relied purely on concepts because that resistor at the end was a pain in the butt. But all in all, I still classified it, and I hope this helps.